Good morning and welcome back. Today, I would like to finish chapter 2, which is one-dimensional motion, and do a few examples, and hopefully move to chapter 3, which is about vectors. And then after that, it will be chapter 4, which is motion in 2 and 3 dimensions. And after that, we will get to Newton's laws. So let's finish chapter 2. So last time we started talking about motion at constant acceleration. We know what acceleration means, we know what velocity means, we know what displacement means. So position is the location of an object in space. Displacement is the final position minus the initial position. The average velocity is the displacement over time. The instantaneous velocity is the derivative of the displacement over time, and the acceleration is the change in velocity. The average acceleration is the change in velocity over time, and the instantaneous acceleration is the time derivative of the velocity versus time. And so, let's see here. We will focus on acceleration being constant. Acceleration is constant. Okay? And we derived the following equations. We said, by definition, the acceleration is the time derivative of velocity. And if we integrate both sides, if you integrate this with respect to time, right? If you integrate both sides with respect to time, you would get, let me move this a little bit. Here I have acceleration. If I integrate both sides with respect to time, on this side I get AT, and here I will get the velocity plus some constant, some arbitrary constant, right? The velocity at plus some arbitrary constant. Let me move let me just write the constant on the other side. So I can write it as plus C, minus C plus C. It's some constant. And so what is this constant? If you plug in a t equal to 0, if I plug in a t equal to 0, so V0 will be, if you plug in 0 here, you get 0 plus a constant. So that constant is the velocity at time t equal to 0. So it's just the initial velocity. So it is simply equal to V initial. And so we write V is equal to the constant, which is V initial, plus the acceleration times the time. So that's how you write it. And then we can also say, by the way, the velocity is the time derivative of position, so dx dt is dx dt is equal to v initial plus a times t. And if I want x, I can integrate this with respect to time. And if you take the derivative of x with respect to time and then you integrate it, you just get x back plus a constant. The constant I'm going to throw on the other side. I'll just write it here at the end. Let me integrate this. This is a constant. V initial is some number, right? The initial velocity of the object. So the integral of a constant is just a constant times the integration variable, which is t. So you get v initial times t. And then plus, the integral of at is 1/2 a times t squared plus a constant, some other constant. If this is some constant, this is maybe c2, another constant. I just give it a simple c. And now what is that constant? If I evaluate the position at t equal to 0, I get, well, if you put 0 here, you get 0. If you put 0 here, you get 0, right? If you plug in t equal to 0. And so what's left is the constant. So that constant is simply x initial. And so we write, by the way, let me box this one. We write here, therefore, x is equal to c, which is x initial, plus v initial t plus 1/2 a t squared, plus v initial t plus 1/2 a times t squared. Okay. So that's that. And I mentioned also, you can have a third equation by eliminating the time. So just solve, if you solve for t here, you will get t will equal to v minus v initial over the acceleration. And if you plug in this expression here for t, anywhere you see time, you plug in t, you will get the following result. I'm not going to waste time deriving it. I'm sure you have seen it before. So I will leave it to you as an exercise to derive it. You get v at later time is equal to minus v initial squared. V squared minus v initial squared is equal to 2 times the acceleration times the displacement, x minus x initial. And so these are the three equations that we use usually. All right. I think the book goes on how to derive this expression using calculus, starting from the fact that the acceleration is dv dt, but the velocity itself is a function of position. So by the chain rule, you will get dv dx times dx dt. That's another way to write it. So you get dx dt is also known as the velocity. So you will get here, let me write here, dv dt. I'm sorry, oh, this should say dv dx. So I get on the left, let me put this on the left hand side. So I get dv dx, that's this one. Dx dt is the velocity, and that's equal to the acceleration. And I will integrate both sides with respect to position. I put dx here, and I integrate. And where do we integrate from? Well, we will integrate from the initial position, x initial, to some x at later time. And here, what's the lower limit? Well, the velocity when the position is x initial, that's v initial, and all the way to some end velocity v. And oh, by the way, dv dx is the differential dv, So you will get v dv from v initial to v is equal to this interval. When you integrate this, you get a times x evaluated between x initial and x final. And the integral of v dv, what's the integral of x dx or t dt? It's 1/2 v squared. It's 1/2 of v squared evaluated between v initial to some v final. So what's this? Well, you get a times x minus x initial. And finally here, if you substitute v and v, multiply both sides by 2, and you substitute v at the upper limit minus v initial at the lower limit, you will get v squared minus v initial squared is equal to, multiply both sides by 2, you get 2a x minus x initial. This is unnecessary, because you could get it here by simply, again, eliminating t from this equation by substituting this. Anyways, we have to remember these equations, okay? So why do we focus on motion at constant acceleration? It seems very limiting. The reason is because many things do accelerate uniformly, meaning they accelerate at constant acceleration. And one of them that we experience every day, acceleration near the surface of the Earth for an object falling freely, a free fall, is called the acceleration due to gravity. It's always downward, and so let me draw it. So here is the y-axis. For a free fall, here is the positive y-axis. The acceleration is downward. The acceleration is in the y direction and it's downward. And how much is it? Well, it's equal to negative g, and that is equal to minus, by measuring it, it's 9.8 meters per second squared. Notice that g itself, g, is positive 9.8 meters per second squared. G is the magnitude of the acceleration due to gravity. By the way, it's 9.8. Some books say 9.81. I think here in the Bay Area it's around 9.8, almost exactly. Anyways, the problem usually will tell you what to put. Okay, some problems, in fact, would say assume that it's about 10, basically 10, to make the calculations easier. So how do these equations change? So let's start with this one. If you have acceleration due to gravity and it's equal to negative g, let's modify this equation. that first equation will become x equals to x initial plus v initial times the time, and then plus the acceleration times 1/2 at squared, but a is equal to negative g, so it becomes minus 1/2 of g times t squared. Again, when you substitute numbers, make sure you plug in positive 9.8. The fact that it's downward, we took care of it. I put minus here. Okay. Finally, or before finally, this one here, you get v equals to v initial plus at. V equals to v initial plus the acceleration times time, but the acceleration is g, so minus g times t. So it's exactly this equation, but I replace a by negative g. And so I get this one here. Okay? And then finally this one here. So you get v squared minus v initial squared, v squared minus v initial squared is equal to 2 times the acceleration, but the acceleration is negative g, so minus 2g times x minus x initial. By the way, sometimes people, if you're dealing with the vertical direction, instead of calling it x, they would call it y. It doesn't matter, it's just a symbol. So you can change these to y. Right? So, in fact, let me just change it to y. So that y consistent with this. Just y initial. So we have to know these equations, right? These, or the more general ones, these. They're more general because these are specifically for gravity. These are for any constant acceleration. So here's an example. Say you have an object. Here's an object, and it's at the initial height, h equal to 20 meters. And v initial, you drop it from rest, so v initial is 0. And the question is, when the object falls, you drop it, it will hit the ground. So with what speed will it hit the ground? We're always asking this the instant before it hits the ground. So not after it hits the ground, bounces a few times, and then settles down. Of course, that's 0. We're not asking about that. We're asking about at the instant it hits the ground, what is this? If you have your hand there and this thing falls, you will feel it falling. It will hit you with a certain speed. What speed will you experience, right? The higher it is, the more speed it will hit with. So what's that speed? Well, we can always draw the axes, always draw a coordinate system. So here's my y-axis. So I have y initial. This is y final. This is y final here. Is equal to 0, and y initial here, y initial is equal to what? Well, it's 20 meters. And if you want to know the speed, you can use one of these equations here. Which one should we use? We don't know the time, so by the way, if you try an equation, the worst case scenario, the worst case that would happen is you would have 2 unknowns, and then you would have to go to a different equation. For example, if you go to this equation here, you can use it to find the time, but we're not asked about the time. We're asked about the speed. So let's try this one because it doesn't involve time. So it says, let me use yellow. V squared, I don't know what it is, minus v initial. V initial is 0, so squared, equals to minus 2 times g. G is positive 9.8. Again, the fact that it's downward, we took care of it. We put a minus sign here. And then y final minus y initial. Y final is, what's y final? Well, it's at the bottom, so it's 0. Minus y initial, that was 20. So you get, here, you have v squared is equal to negative 20 times negative 2 is negative 40. I'm sorry, negative times negative is positive, so it's 40. And then 40 times 9.8, so 40 times 9.8. It better be a positive quantity here because it's v squared, and otherwise you would be taking the square root of a negative number, which is a complex number. The velocity should be some real number. So v will be plus or minus the square root of 40 times 9.8. And let me use my calculator. I mean, it will be 40 times 10 is 400, square root of 400 is 20, so this will be approximately 20. So let's see, get 40 times 9.8, and I have to square root that. And I have 19.79, 19.8. Meters per second. It says plus or minus. Which one should we take? Should we take the positive or the negative? Well, in what direction is it moving? As it falls, it's heading downward, so we have to choose the negative because it's going downward. So that's negative. If you were asked about the time, you can use this equation. But if you know the velocity already, if you know v final, you can use this equation to find the time. So for example, let's use that equation. I have assigned several problems varying difficulty for this chapter here. So we can use this equation here. V final is negative 19.8 minus V initial, I'm sorry, not minus, equals to V initial, that's 0, minus G, that's 9.8, times the time, which is T. And so, what's the time? It will be negative 19.8 divided by negative 9.8, and so you get T is equal to over 2.02. By the way, in all of these free fall things, we're assuming the only force involved is due to gravity, and so everything falls at the same rate, whether it's a feather, or it's a piece of paper, or it's a solid ball, or it's a brick. Everything falls at the same rate. So if I release a piece of chalk and a feather, they start from rest and they follow the same rate, so they will reach the ground at the same time, because we're saying there is no air resistance. In experience, in the real world, like here, if you drop something, there is air resistance. And so an object that has a larger surface area will experience more air resistance than a more compact compact object, such as a steel bead or something. Okay. Okay. So usually, again, we will ignore air resistance and so on. So let us look at an example here that I would like to do. And so part of today, I'm done with basically the material of this chapter. So we have a few more, just 3 or 4 problems that I want to do. Okay. So the first problem here, it says a rocket sled's engines fire for 5 seconds, boosting the sled to a speed of 250 meters per second. So here is a drawing of what's going on. So you got a sled. Let me just draw it as a box. V initial is 0. It starts from rest. And then there are those engines that fire, and they will accelerate it, just accelerate it this way. So let me call this here x initial. And this point here is x1. And so at this point, the speed is 250 meters per second. Okay, 250 meters per second, and it's moving this way. Okay. And then what happens? So it accelerates. Then the engines will shut off, and the sled will deploy a braking parachute. And then it starts to slow down. And it slows down at a rate of 3 meters per second, meaning the acceleration is 3 meters per second squared, right? That's what 3 meters per second means, 3 meters per second squared. So it slows down, starts to slow down until it gets to here. I will call it x3, and and then it comes to rest. V here, let me call this one here V3 equals to 0. And this one here is oh, 0, 1, let me call this one x2. This is v2, and this is v1. So first of all, what's the acceleration here, and what's the acceleration here? First, the acceleration here would be negative because you're slowing down. Why? Let's see why. Let me pull out this formula. If you have a velocity, and you would like to increase the velocity, right? If the velocity is positive, and you would like to increase, if this is a positive quantity, to increase it, you would have to add to it, meaning the acceleration will be positive, right? Now, if you want to slow down, let's say your velocity is positive, your initial velocity is positive, as in the case here, it's 250, and you would like to slow down to 0. So you have 250 here, and I would like to make this 0. So if this is 250, I have to subtract from it 250 to make this 0. So if the velocity is in this direction, the acceleration has to be in this direction to slow down. If the velocity is this way, let's say this is positive, the acceleration has to be negative in order to slow down. If the velocity and acceleration are in the same direction, you speed up. Same direction, this way, this way, this way. If the acceleration and velocity are in the same direction, you speed up. For example, if I throw this piece of chalk upward, the velocity is in this direction. Guess in what direction is the acceleration? It's this way, acceleration due to gravity. So as the chalk goes up, the acceleration is this way, so it slows down until it reaches the top. The speed will be 0, and then it starts to drop. When it drops, the velocity is also downward. It's heading down. The acceleration is down, so as it drops, it speeds up. So when the acceleration and velocity have the same sign, you speed up. If they have opposite signs, you slow down. Okay. So at this point here, the acceleration here, let me write it in yellow. Let me call it A2, is minus 3 meters per second squared. I don't know what A1 is. I don't know what it is. Okay. I put a question mark there. So what's the question? You start at 0, you accelerate, you reach 250, and then you start slowing down until you stop. The question is, what is the total distance traveled? So from here all the way here, what is the distance? So we will do it in steps. We will find x1, and then from x1 we will use this acceleration to get to x2. Okay. So I need to find what acceleration 1 is. And I'm assuming that the acceleration is constant. It's a constant acceleration. So let's use, for this step, it's motion at constant acceleration. So I know that I can use those 3 equations. I know that v is equal to v initial plus the acceleration from here. v1 is equal to v initial, let me label it correctly. v1 is equal to v initial plus the acceleration times the time. And the acceleration is a1. And acceleration times the time. And I should call the time to go from here to here, I would call it t1. That means the acceleration, a1, will be v1 minus v0 over t1. Okay? And then I substitute. v1 is 250. V initial is 0, it started at 0, divided by t1. Well, how long did it take it? It accelerated for 5 seconds to reach this, so the time is 5. And so it would be 250 over 5, and 250 over 5 is 50 meters per second squared. That's a very large acceleration, like 5 times that of gravity, 50 meters per second squared. So I will use that now to find the position here. Again, I can use, for example, one of those 3 equations. I want the position. So let's try this one here. So I will write x1 is equal to x initial plus v initial times the time plus 1/2 of the acceleration. But I have 2 accelerations here, so I have to specify acceleration 1, and I have the time squared. Oh, I should write t1 also. So I get x1 is equal to x initial. What's x initial? Well, I can call the starting point to be 0. I'm free to choose the initial point to be the starting point, because I just want how far is this from here. So if I start counting from 0, and this is 100 meters, then it's 100 meters away. So, x initial, I put 0. V initial, it was 0. T1 is 5 plus 1/2. The acceleration, we just found it, it's 50, 1/2 a1. And then the time is 5, and you square it. 50 over 2 is 25, and 5 squared is 25, so it's 25 times 25, which is 625 meters. So I will label it here, since we found it. So this is 625 meters. This one I still don't know. I do not know. Oh, this one we know it now. It's 50. Yeah, 50 meters per second squared. So now, from here to here, I need to find x2. Well, let me write down the equation. I know that x2 is equal to x1 plus v1, v initial, right? If this is my now new x1, right? The equation says x equals to x initial plus v initial t plus 1/2 at squared. For this time interval from here to here, this is my initial and this is my final. So the initial here is the initial velocity here, so it's v1, which is 250. And then x1, and then times the time. The time I'll call it t2, I don't know what it is. And then plus 1/2 of the acceleration, 1/2 at squared. Which acceleration? It's a2. During this time interval, going from here to here, a2 applies. a2 t2 squared. But the problem is, to use this, I have two unknowns. I don't know what x2 is, and I don't know how long it will take it to stop. So I better find the time first. See what happens. I got stuck, but that's fine. I will just leave this equation here with like a star next to it. Let me try something else. I know v initial here, the velocity during this interval from here to here, the initial velocity is v1, which is 250, and the final velocity is v2, which is 0. And I know the acceleration, so I might have good luck or better luck using this equation. V final equals to v initial plus at. So I would write v2, v final is v2, equals to v initial is v1, plus the acceleration times the time. The acceleration during this period, we're calling it 2, and the time is 2. And I would like to find the time. So the time, t2, would be v2 minus v1 over a2. So the time, t2, would be v2 minus v1 over a2. So let's find it. v2 is 0 because it stops. v1 is 250, and the acceleration is minus 3. So it'll be 250 over 3. 250 over 3. Some number, I don't know what it is. I don't really care about that number either, because I'm going to substitute it in my calculator. So now we can use this equation here. So I would say x2 is equal to x1. x1 is 625 plus v1 t2. v1 is 250. t2 is that number, 250 over 3. And then plus 1/2. a2 is minus 3. And then t squared, but t is 250 over 3. Okay? So now we can use our calculator to do that. And using the calculator, I believe you get around 11,000. Let me just write it down. Yeah, it's about 11,000. 11,000 meters. So, I will pause this video here, and then we'll continue in the next video with 3 or 4 more problems, I believe.